I'm good to go. Oh, okay. Sorry. So thanks for having me here. Just like Tim, I'm one of the people from the other program as well, and I'll tell you a bit about a bunch of problems that some of us have been looking at on optimization under uncertainty. And some of this will have strong parallels with what Tim talked about, and I'm not going to point them out one by one, but you can draw your own parallels, and we can talk about it offline as well. Because I realize I'm the only person between you and lunch, right? So I should. Good. So, and it's also going to be, the talk's going to be somewhat light on sort of proofs and technical details, but again, I can fill you in offline. So the premise is that optimization problems are often defined on uncertain data, and this is not an audience which needs much convincing about this thing. Data might not be available. We might just have predictions about the inputs. The actual data will arrive later. You want to do the work right now so that you're prepared for when the actual data arrives. Or actual data might not be possible to get. It's just difficult. It's time-consuming. We essentially have predictions, and we want to deal with it, right? And you can write down many other reasons why you want to look at optimization under uncertainty. So given that, what should we do? So this is, the field of optimization, the field of algorithms has been around for a long time, and people have come up with various solutions, right? I mean, one of the solutions is actually, you don't deal with it. You actually just do offline algorithms where the input is given. It's the stuff that we talk about in our textbooks. The input is a well-defined set of numbers, and you want to sort them. And the input is precise, the output is precise, everything's very nice. And I'll call this a know-everything model. It's deterministic algorithms. Maybe I should even say randomized algorithms. I'm not differentiating between deterministic and randomized in the sense of whether the algorithm flips coins or not, but whether the input is deterministic. Okay. And perhaps too optimistic. I just convinced you, or maybe I didn't convince you, you needed no convincing, that we need to study, we need to handle uncertainty, and then I give you a model which doesn't handle uncertainty. So very unsatisfying. Or a model which has been very popular and successful, and a beautiful model, is that of online algorithms. And just in case you haven't seen it before, here's a one-slide primer about online algorithms. The instance is revealed slowly over time. And you need to make irrevocable decisions before the next arrival happens. So a bunch of paging requests happen. You need to figure out which page to kick out of your cache. And this is the gold standard out here is the competitive ratio, which says, hey, you have an algorithm that's working without knowing the future. It's making decisions on the fly. It has some cost. And then you look back on an instance, for a given instance, you look back and you say, what could you have done if you knew the instance completely? In hindsight, what could you have done? And this is the offline optimum, and you compare the two. And you say, well, what's the worst case ratio between the two? Right. And if this ratio is small, then you know that your algorithm is pretty darn good. Even if you had known the entire future, you couldn't have done much more than whatever this ratio is. But this is from Slater and Tarjan in '85. You're competing with the best solution in hindsight. So this is a model which is very popular, and it's perhaps one of the reasons why we've one of the reasons people have studied this a lot is it gives very strong guarantees when it gives positive guarantees. But again, it has the same problem that very often it gives results which are too pessimistic. And then you don't know what to make of it. All your paging algorithms are just as bad in every instance, on the worst case instance in particular. So in that case, you don't know what to do. And one of the things, and this is in keeping with the sort of previous talk, is that often you assume something. You assume that you know something about the input. You don't assume nothing about the future. So this is, you can call this stochastic optimization. You can call it Bayesian optimization. And that's the main idea that I'm going to talk about today. And perhaps you can think about this as a sort of yin and yang thing, right? It's actually, it's more complicated than a know-everything model. But on the other hand, it's a weakening. It's a substantial weakening of the know-nothing model. And you can view it whichever way you want. You want to view it, as a sort of a pessimistic thing from the from here or as an optimistic thing from here, that's your choice. But I'm just going to tell you the models. I'm going to tell you a bunch of problems, and we'll take it from there. Okay. So I'm going to just tell you about 4 problems, and I'm going to tell you the problems up front, and then we'll see how much how much detail I can tell you, or we'll play it by ear. Okay. So the first problem is a problem that Tim alluded to at the very end of his talk. It's a knapsack problem. So a knapsack problem, all of you know, you're given a bunch of items. The items have a certain size, and they have a certain value, and your knapsack has a certain bound. And you want to pack these items into this knapsack. And this we know exactly how to solve, right? We teach this in our undergrad classes. But now the item sizes are random. What are you going to do? There's a different one. You want to build a network connecting customers, a cheap network. If all the points you wanted to connect were known up front, this is known as a Steiner tree problem, we kind of know what to do. But what's happening is that the customers are arriving online, let's say, and each of them is a random draw from a given distribution. What are you going to do? Okay. You want to find large matching in a graph. But actually, you don't really know the edges of the graph in some sense. All you can do is, given a graph, you say, okay, I'm going to match these 2 people. And then you find out whether the matching was successful or not. And this is, by the way, something that comes up in kidney exchange. It's a very popular problem right now. You try to match donors and recipients, and sometimes it succeeds, sometimes it doesn't. And then you want to figure out, how do you find a large matching in a graph? So, and here's a different one. You want to serve customers. There's a bunch of people waiting outside in the foyer. You want to serve them. It takes you 1 unit of time to serve a customer. Each customer has a certain value, so you pick the highest value customer, let's say. But the people who are waiting outside, they're kind of impatient, and they leave. What are you going to do? Should you pick the highest value person to serve? Or should you pick the second highest value person who has almost the same value but is much more impatient? So I just gave you 4 problems I could have, and in fact, each 4 of these I could, refine in many different ways. I could give hour-long talks on each of these. So this is just to give you a sense of the kind of problems we're interested in. These are all very simple problems on the face of it. But uncertainty causes these problems to become somewhat more complicated. And thankfully, we can do sort of interesting things in each of these cases, and I'm going to tell you what we know about some of these. Some ideas. So let me put down the goal. The goal is to design algorithms that make near optimal decisions. And the near optimal is just alluding to the fact that some of these problems are hard. Maybe the hardness is due to the uncertainty. Maybe the hardness is due to just the underlying computational problem being NP-hard. And I'm given certain predictions, some probability distributions. And we can talk about how much of the probability distribution do you need to know. Do you really want to depend on the priors, or do you want to be prior independent? It depends. In most cases, we'll give approximation algorithms for these problems. In some cases, the optimal solutions are known, but actually all the stuff I'll talk about today will give approximation algorithms. So you should think of this as, still it's worst case analysis, but the inputs are distributions. Okay. And I'll try to make this a little more clear. And the sort of questions that you should ask yourself are, how do you model the uncertainty? How does the solution space change? And how do the solution techniques change? Because we really do want to solve these problems. And the history, very quickly, stochastic optimization's been around since at least the 50s. Many textbooks, in fact, lots of great heuristics. And those of us coming from the theoretical computer science area, it's natural for us to try to explain their effectiveness or come up with algorithms that at least work well with provable guarantees. Okay. And the approximation algorithms effort is a little newer, and I've put up a few references, but let me not spend time on them. Let me just tell you what I'm going to do. I'm going to tell you about the stochastic knapsack problem. It's a well-defined, crisp, clean problem. Maybe I'll give you a few details about it. I'll talk about stochastic Steiner tree, which is a simple network design problem. And then I'll talk about maybe a bunch of little short things, depending on how much time we have. Okay. So maybe I'll just go back to this slide and just pause for a second in case there are any questions about this. Good. Okay. So let's dive in. Let's talk about the first problem. So the first problem is the stochastic knapsack problem. And what's the deterministic knapsack problem? This is something you know. You're given a bag. The bag holds a total size of B. And you're given items which all have a certain size. And I'm denoting the size by kind of the height out here, and a value. And you want to pick a set of items to put into your bag so that their total size is no more than the size of your bag, and the total reward is as high as possible. And we know there's greedy-like algorithms which give you approximations. There is dynamic programming-based algorithms, etc. Okay. So the stochastic questions are, or one of the stochastic questions you can ask is that the sizes and rewards are random. So instead of the size and rewards being known up front, they're random variables. And what your input now is the distribution over size-reward pairs. Okay. So what can you do? And here's one model which was proposed about 10 years back. Is essentially all you're allowed to do is you're allowed to take an item and put it into your knapsack. And then the size instantiates. Okay. So let me show you an example. All you can do, okay, what's the input? You're given a knapsack, fixed size. You're given a bunch of jobs. This job is this size, but gives you no value with 0.4 probability, and this size and gives you $10 with 0.6 probability, etc. Jobs might be deterministic, so it's a generalization of standard knapsack. And what are you allowed to do? You're allowed to point at the job. You say, I'm going to run this job. The job runs. It takes up certain size. It gives you certain value. And now you say, what are you going to do? I pick another job. I put it in. Get some size, some reward. I see what I get. And that's all the information I know.
So what, you know nothing in advance?
You know the distributions in advance. Absolutely. And now, at this point, you might say, OK, I'm going to take this job and put it in. You're kind of hoping that you'll get these sizes. But you're unlucky. You get that size. You've exceeded your knapsack size. The process stops. You don't get any reward. Just think of running a bunch of jobs whose size distributions you know.
But in this case, the reward is 0 or 8?
In this case, which case was this?
The last item is a failure.
Oh, so the last item was a failure. You get 0 reward for that.
On the total thing, or?
No. So every reward that every job that finishes, you get its reward. Yeah, totally. Good. Is the problem clear? Okay. Good. So in some sense, all you're doing is at each point in time, you're kind of resolving the uncertainty. You say, tell me more about how long this job's going to take. And the only way you do is by running the job. So, maybe I'll skip over this. You can imagine that online algorithms are completely, you shouldn't compare yourself to the best solution in hindsight. A solution that knows the outcomes of all the jobs. Because, hey, there could be many jobs, and one of them is going to come up of a tiny size. Maybe I'll show you the example. There's n identical items. Each of them take on a huge size with, almost certainly. You'll never finish this job. But with a very tiny probability, it takes on size 0. You will finish this job. So if I have n jobs like this, with constant probability, one of these jobs will be size 0. So the optimal solution, which sees everything, can pick that job. But you have no chance, right? All you can do is just try a job and try a job. Okay? So what we want to do is, in this case, you want to make sure your algorithm's performance is compared to the best algorithm of the same type, which has the same information, an apples to apples guarantee. Okay.
What is the best algorithm?
What's the best algorithm? Good. So the best algorithm is a decision tree like this. It says which job should you try first, and then depending on the outcomes, it gives you the next job to try. I mean, it's the obvious thing, but once you see it, you're like, yeah.
Seems like the only thing. I mean,
what else could we compare it to? Yeah. Either we compare to the best algorithm in hindsight, which we don't want to do for obvious reasons. This seems like a very reasonable thing to compare to. Okay. Well, actually, you could compare to something. Maybe I'll come back to this. You could say, okay, so this, you understand what this is, right?
So why can't this be your solution, your actual algorithm, not the benchmark, but the real algorithm?
Yeah, so that's the problem, right? I could find the optimal solution, but the optimal solution itself could be exponentially sized.
It's complexity.
Exactly. So these problems, for those of you who work in this, are usually finite horizon MDP type problems. And you actually solve these things. Oh, I'm assuming that the distributions are given in some succinctly represented way. So you can solve these things given exponential time, but maybe we don't want to do that. So there are a bunch of hardness results as well, and it's easy to cook up examples where the optimal decision tree is exponential sized. So then you say, maybe I want succinct solutions. So let me just introduce two pieces of notation. A decision tree I'll call adaptive if it's a decision tree. And here is a solution which I might hope for, which is simple to describe, which is just a list of items. I say, try item 1. When it finishes, try item 3. When it finishes, try item 2. And if I run out of time, I run out of time. Okay. A decision list, if you will. And this will have some value. And there'll be a gap between, this I'll call a non-adaptive solution. It's not adapting to the prior outcomes. Okay? And then I ask the question, one question you could ask is, what is the price of adaptivity? How much do you lose if you restrict yourself to non-adaptive solutions? And then we could ask for actually mildly adaptive solutions. You could say, compare myself to the best decision tree of polynomial size. I have no idea how to analyze those things, but there's some work that's kind of approaching that direction. Okay. By the way, so the problem clear? Is the solution concept clear? The solution concept, we want to compare. Okay, so maybe here's an ideal situation. An ideal situation is, give me a non-adaptive strategy which compares favorably to the best adaptive strategy. This would be the best of both worlds, right? Best of all worlds. I don't know what both worlds are. But, okay. So here's one approach. Here's the first idea you'd try, maybe. At least the first idea I would try is, I have random sizes. Let me assume that the sizes are random, the rewards are fixed. There's some complications with that. I might allude to that later on. Okay. Sizes are random, rewards are fixed. Okay. Replace each job by a job of the right size, right expected size. And now this is a deterministic problem, just solve the problem. Good or bad?
Bad.
Bad, yeah, terrible. Expected size is too sensitive a statistic, right? I mean, why should you look at the expectation? Basically, here's an example. This bin size is B always. Here's one item which is almost always 0, but with some small probability, I'll give you a massive size. So, I can make its expectation anything I want. Okay. So what should we do? So you observe that, look, basically if your size is more than B, the bound that you want, it doesn't really matter if it's slightly more than b or a huge amount more than b. Right? So here's something very simple. I'll show you only the simple things. This talk has been chosen, the problems and the examples have been chosen to make these possibly digestible in 40 minutes. Okay? So here's the simple idea. Take the size, but truncate it at b plus epsilon. The size went to b plus epsilon, I don't care what the size was. Okay? And that's our expected size. It's a virtual size. And the reward should also be truncated suitably. I'll get a reward only if the size, less than equal to b. Be happy with that, right? This should be, I'll get reward only if the size is less than equal to b. Okay. So that's the virtual reward, that's the virtual size. And now you use a deterministic algorithm, find a good solution. Okay. And there's a slight twist. You almost use this. So here's one algorithm. With probability half, try all these jobs in random order. So this gives you a list. Just try these jobs in random order. And with probability half, just try to place the best single job in your system. For some technical reasons, you have to do one of the two. Morally, you should just think of this. But actually, sort of morally, you should also think of the fact that, morally, you should just think of this. Don't worry. Okay? And this was a very nice theorem due to Dean, Gomans, and Wondrak. And they showed that this is a constant approximation. As in, this gets a constant factor of the optimal reward. And the optimal, remember, is the reward of the optimal decision tree. So I'm saying, with 50% probability, you just try one job, and whatever you get, you get. With 50% probability, just try the jobs in the optimal deterministic solution for this one. You're kind of hedging between these two strategies. But both are non-adaptive, simple strategies. Does this make sense? Is everybody just hungry? But questions? So here's a question that, how would you compare this to the best decision tree? This is the question that, really bothered me at the beginning. When I look at this problem, I need to compare myself to the best decision tree. How do I even reason about the best decision tree? It's this exponential sized, humongous object. The answer turns out to be simple. By the way, this was a non-adaptive strategy, and the adaptivity gap is bounded then. So how do you compare yourself to the best decision tree? And the answer is you use linear programs. Now, this is an idea that a lot of us are comfortable with, where we use this all the time. But here is an example. So you write down a linear programming-based algorithm. Okay. So let me give you a way to reason about that particular algorithm via linear programs. But actually, what I'm going to do is I'm just going to write down a linear programming-based solution. So I'll say maximize the total expected reward. Rewards are constant, so you can imagine that the expectation's not there. Okay? So maximize the reward. Think of xi as a variable which indicates whether I was chosen in your solution or not. And such that the expected size, and you should think of this as the expected truncated size, of course, is at most b. Okay. This is a linear program we write down for knapsack, just for knapsack. For stochastic knapsack, the meaning, the linear program remains the same. The meaning is slightly different. Xi is now supposed to indicate the probability with which you try item I. So this linear program, you can show, captures the optimal strategy. Why? Well, essentially, linear program, the optimal strategy satisfies the following. Imagine one outcome of all the random variables. Then the size, and this is a particular outcome of these random variables, times whether you added this to the knapsack or not, is at most b plus the outcome, the size of the last item. Because the last item you added, but whoops, you went over. But the last item, because we truncated the sizes, is at most b as well. So it's at most 2b. So for every outcome, this constraint is satisfied. So in expectation, this constraint is satisfied. But what's the expected constraint? It's that constraint times 2. But yeah, what's a factor of 2? So maybe I should mention, all the constants I'll show, all the analyses I'll show out here are not the best analyses possible. But again, I'm not trying to optimize constants. I want to give you the general idea. Okay? So somehow this LP captures the optimal strategy. In particular, I should mention, it captures the marginals of the optimal strategy. And this idea, by the way, is not particular to this example. One of the things Tim mentioned was this optimal auction of Roger Myerson. And you can view his optimal auction as basically writing down such an LP, a much bigger LP, but the same kind of LP with variables only for the marginals. Is this item allocated to this person or not? So the idea of using LPs is fairly general, very powerful. And then what you do is you round this LP, and you get a solution out of it. And the solution essentially gives you the algorithm from the previous slide. The analysis is very simple. It's via Markov's inequality, but we're short in time, so maybe I won't go into that. You can extend this to random rewards and sizes. What's the takeaway? The takeaway is, the idea is, stochastic optimization might seem like a completely new field, but very often the ideas are very simple. They're very similar to things that we know. They're simple in the sense that they're not completely out of left field. So you can use techniques that we know to solve these problems. You have to be a little careful. You want to be careful in how you deal with the random variables. And in some nice cases, you can find a non-adaptive strategy that is comparable to the best adaptive strategy, as in this case. So basically, for the rest of the talk, I'll just tell you about a few problems, and maybe try to convince you that these problems are interesting. And there's a whole bunch of work that still remains to be done. Here's a slightly different problem. I leave home at 9 o'clock in the morning. I need to run a bunch of chores. I leave home at 9 o'clock in the morning. I have to do a task. I have to go to the bank, to the post office, to the, whatever. The shops close at 5. The time budget that I have. I know the time it takes me to walk from place to place. Okay? What I don't know is when I get to the bank, how long will I have to wait before I'm served? It's a random variable. But I've been to the bank so many times, I know the distribution of this random variable. What should I do? Okay. It's a problem I do face once in a while. It's a problem I'm sure all of you have faced. What should you do? Well, what you can do is you can get a result, and I need a little more time for this, so we'll do this offline. I can give you a non-adaptive strategy that in the beginning of the day, you're going to flip some coins, and you're going to write down a list of things. You're going to say, I'm first going to go to the bank, then the post office, then this, then that, and just try this in this order. And the solution you'll get will be kind of close to the best solution, best adaptive solution. And then you can say, well, this might not be so good, right? But sadly, we can also show some lower bounds. and this is work that Vishwanath and Nikhil Bansal have done, is that there are problems for which the adaptivity gap is large. So if you restrict yourself to just writing down this list of solutions, the list of things to visit in that order, you might get a poor guarantee. And a very natural question is, can you write a mildly adaptive solution of polynomial size that actually gives you a much better guarantee? Actually, another very interesting question along these lines is, the random variables at the banks and the post offices, they're not really just random variables, they're little stochastic processes. They're little lines out there. I go to the bank, I see a long line. Maybe I come back, the length of the line should be correlated with what I saw earlier. And depending on the time difference between when I first saw it and when I second saw it, the correlation should decay with time. What can I say in that case? What if travel times are random? So all these problems are open. I urge you to try them. I'm going to ignore the approaches for this one. The moral, I can tell you, we reduced again the problem, the stochastic problem, to a deterministic one. It wasn't the most natural deterministic problem, but this was a fairly natural problem to solve. And again, we found non-adaptive strategy. It's an open problem to relate it to the best, to find an adaptive strategy, which is pretty good. And maybe, yeah, go ahead.
Just a basic question. So are you looking for p-time algorithms? Are you looking for some, or in BPP, are you looking for something in BPP to the NP?
I'm looking for p-time algorithms. A BPP is fine. They're allowed to flip coins, but I want a succinct representation of the solution. And I want this to be computable in polynomial time. So, yeah, 5 minutes? Okay, good. So, what I'm going to do is I'm going to let me try to get to let me tell you about these couple of problems. Oops, I don't know why there's a massive feedback out there. Good, okay. So let me tell you about this problem that I particularly like, and it has very natural open problems in there. Sorry. Okay, here's the problem. The problem that I mentioned at the beginning of this talk. I have to serve a bunch of customers. Each of these customers has a certain value, but they're all somewhat impatient. Some of them more impatient than others. This person is a saint. They have no desire to leave. They just want to check out the Wi-Fi in this place. This person has an important appointment. They'll leave almost immediately, and you see, more impatient, less impatient. And now, each point in time, you pick a customer and you serve them. So you say you pick this customer, you get their value, but every other...
No, it's not you. The system just crashed. So
Oh dear.
it's supposed to crash at a certain time.
Oh, excellent. Maybe I'll turn off the mic then in that case.
Then
Should I turn off the mic?
No, then they are not recording you that.
Cool. Okay, so sounds so much better. Thank you. So you serve this person. Each other person flips a coin with the given probabilities. If the coin comes up heads, they leave. Okay. So in this case, maybe this person left. These two people are still remaining. You pick another person to serve. Other people flip their coins again. They leave. So I'm basically imagining a situation where there's a bunch of people sitting around, and they have impatience and they have departure probability. There's a model for their departure. what can you solve? How much value can you get? You want to maximize the expected value. So what's the strategy? This is the last, what's a good strategy? Oh, what's the strategy? Suggest anyone.
Greedy.
Greedy. You can be greedy on two things. I'll try the first one. Greedy on the value. Just pick the person with the highest.
Or on the expectation.
Or on the expectation. So if you try greedy on the value, you get a factor of 2. Because each time you pick somebody, that person might be a saint. They'll stay in the system forever. But instead you missed out on somebody who's very impatient. You could have got their value, so that's a factor of 2. And you can show this is, you can't do any better than a factor of 2 using this strategy. Greedy on the expectation, unfortunately, turns out to be arbitrarily bad. Okay. Yeah.
Question? Only one person leaves?
No. So in this example, only one person leaves at each point in time. But basically, everybody flips their coins, and whoever gets heads, they all leave. So if the coins were unbiased, about half the people would leave. If you try, some randomization, you can get 63%. If you try harder, you can get about 70%. But guys, I don't know whether this problem is NP hard. I don't know whether this problem has a, what I do know is that this problem doesn't have simple index policies. As in, if you just assign each person based on their value and their probability a single number, and pick the person with the highest number, that's an index policy, this jargon. No index policy is good. No index policy is opt. Index policies could be close to opt. I don't know how it's opt. So I'm going to stop now. Basically, I wanted to give you a sense of a few problems where stochasticity added to very well-studied problems, so problems that we know and love, actually give rise to very interesting twists. These are algorithms. Often we can get algorithms by reducing to the right deterministic variance, but in some cases we don't quite know. It connects to a rich body of work in multiple disciplines, but there's still some new ideas that come in particular because we want to handle the the exponential, the fact that we want to run in polynomial time is very computer sciencey. Question?
But I want to go back to Dan's question. Suppose you allow yourself a deterministic optimizer.
Deterministic optimizer.
Offline optimizer.
Okay.
For
for the underlying
problem. If you know everything, you solve NP. You solve the optimization problem. So you have the deterministic optimization problem as an oracle. Because that will somehow tell you what is the cost of the stochasticity.
Fair enough. So.
I think that's what you're asking.
Good. So what you want to do is you want to say, suppose I could solve the underlying deterministic problem in polynomial time.
No, I have an oracle for solving
Exactly. Exactly.
Yeah.
The knapsack. Suppose I can solve
Yeah.
knapsack exactly.
Yeah.
What can I do? So like for knapsack, I don't know better than a factor of 2. Against, even if I had an optimal solution for knapsack. If you insist on writing down the optimal strategy, then you can show that for certain variants of knapsack, the problem is p-space hard. But it would be nice to be able to say, assuming if the approximation guarantee in the deterministic case was alpha, then I can get 1 plus epsilon times alpha. I know this only in very, very specialized cases. Good. So that's pretty much it from me. Thanks.
We are running out of time. I propose we stop here. It's lunchtime, so feel free to discuss over the long break. And we resume at 2 o'clock.